Well, that's just concerning. How are you guys doing? Whatever boogeyman is out injuring people hasn't got to you guys yet.
Not yet.
No, this boogie person shall not. We shall all be okay. All right. So the chapter 16 homework quiz has been moved to tonight, in case you guys have any questions this morning. So we'll open with that, and then we'll continue talking about electrical current and resistance. So, any questions about anything at all related to chapter 16?
Did you upload this on Brightspace?
Sorry, these notes are still not on Brightspace. I apologize for that.
Whoa, I have a question.
Yeah? Okay, well, okay, hang on. In the order I was asked,
Yes.
not on Brightspace yet, because I was reorganizing how I was teaching things, like the order, and maybe pulling some things from chapter 18 in to this set of notes, so I was still rearranging things. And last couple of days have just been kind of crazy, frankly, because on top of work, there's also been wedding planning, home improvement
When do you get married?
this summer,
Like when?
June.
My cousin gets married in July. There's a lot of weddings. That's
Yes.
like the fourth wedding I hear.
Well, everyone who was going to get married last year is pushing it off till this year. The notes aren't up yet because I was still tweaking them and I got kind of carried away with other things yesterday, so I apologize for that. I'm trying to get them up today. Next question, sorry.
So chapter 16, right? So you edited it and you added another question?
Correct.
Let me just show you what it looks like. So like I had already finished it, right?
Yes.
And then, so like I have 100, but I never did the last question because I'd done all the other questions.
Yeah, your grade was set before it was added.
So
Oops.
what does that mean? Do I have to do number 9?
I would like it if everyone did. Hang on, let me check real quick. Keeping in mind the edited point values. Did you not post that quiz? I've never seen that before. I'm curious as to how this works.
Look, for number 4, I got more points than out of 2.
This website is a hot mess.
Because like you said, I had already done it when it had different point values.
Right.
So I don't know if it like kept it.
Now you've already got a grade in. It's fine to keep it that way.
So, like, it still said like 100 on your end,
Yeah,
it's not just mine.
double check. Last name again, sorry.
Martinez?
Well, on my end, it says 25.5 out of 26. No, now it says 25.5 out of 25.5.
What?
I don't know, maybe the grade book page is rounding.
Okay, I refreshed, and it says the same, 25.5 out of 25.5.
Okay.
So what do I do?
You can leave it.
Okay, cool, thank you.
I'm more intrigued by the situation than mad.
Yeah, it's pretty weird.
Any negative emotions I'm feeling are webicide for being webicide. So that's interesting. I'll have to keep that in mind. Okay. Thank you for telling me that. Any other questions from that assignment before we look at chapter 17 today? Okay. So, current and resistance. Is anyone here not at time yet this week? Okay, so this will add additional information to what we see today. So, I forget exactly what I said to which lecture, because,
We never like did the PowerPoint. I think you just like kind of like wrote stuff.
yeah, I skipped around a bit to start showing the circuits that we need in the lab that week. So I'm backstepping a little bit to go back to the official start of the basics of the chapter. Let's define what electrical current is formally. It is defined as the rate of electrons, current is charge flowing, and it's the measurement of the number of charges flowing in an amount of time. The more electric current you have, the more charge is physically moving through the system every single second. So the variable for current is I, weirdly, and that is equal to the change in charge, the flow of charge per unit time. So you could write that as current is equal to coulombs per second. And did I mention that this part is Edison's fault? So,
Oh, yes.
yes?
Yeah. Because it like shows it as like the flow of protons, but it's like electrons.
Yes, every single thing in electricity is written from the proton's perspective, even though what really happens is the electrons are moving, which is infuriating. And it's all because Edison arbitrarily decided the ones over there, like I did this experiment, I separated the charges. These ones are plus, these ones are minus. I'm going to treat these ones as if they're the thing that's happening, and it's not.
But it's like wrong.
It is wrong. Protons only move if they're loose in the universe. And if they're loose in the universe, that's just hydrogen gas. If it's just a proton, it's specifically a hydrogen ion. And it will probably pretty quickly bond to something else. So you will very rarely ever see a single proton by itself doing anything other than reacting or burning, which is also reacting. that said, what really happens is electrons flow. So I'm going to describe it as the number of electrons passing, or charge of the electrons passing per second. More charge, more electrons surging through something. And the unit for current is amps. You've probably heard this term before. There's a lot of electrical terms that get thrown around, like watt and volt and amp. And this specifically refers to current. I think it is short for ampere gesundheit, which is the name of a scientist. I forget the full name though. And the current, since this is the actual amount of electrons moving through something that's being electrocuted, the current is the dangerous part of electricity. Because if the current is high, that's more electrons passing, if heaven forbid you were a person, if you were being shocked. The higher the current passing through you, the more electrons are surging through you. And that means they're carrying and leaving more energy behind. You could be exposed to 10,000 volts and nothing would happen if there's no current. So high current is dangerous. 1 amp alone is already dangerous. So the circuits that we're dealing with in lab this week and all the currents in my phones and most consumer electronics are set to the scale of milliamps. Additionally though, most appliances use a voltage that's so weak it can't hardly push any electricity through the resistivity of your skin. So, having this, we're right there real quick. Keeping that particular model in mind. A circuit has 6 milliamps flowing through it. Over 1 minute, how much charge is going to exit the battery in this circuit?
That was 10 seconds.
Yes. The units here, we have 1 amp is equal to 1 coulomb per 1 second. Those are the units one should use. So what values for C are we getting? Very good. Units should be in as they should. I was using the unit for the variable again. Doing that more frequently now it seems.
That was on purpose.
All right, 0.36 coulombs. How can we figure out how many electrons that is? Actually, sorry. We're going to add a negative there because we know realistically that these are electrons. They will have a negative charge. Make sure that my sign doesn't take any points away because of details like that. With this in mind, how many electrons would this be? Or how would we be able to find that out?
Well, like, we know the charge is 1 electron, so can you just divide 0.36 divided by the charge of 1 electron?
Almost. We do know the charge of 1 electron. I'm just going to set the conversion up real quick to make sure. So, yes, you're right. We would divide by the charge of 1 electron. So that would be negative 1.67 times 10 to the negative 19 coulombs, 1 electron. And that would give us a much, much larger answer. Do you agree? All right. So, proof of concept for the definition and formula for current by itself. And current and volt. Okay, so look at this circuit for a second. We have battery, which provides a potential difference, a voltage, one side to the other. Let's say this is a 9-volt battery. That means one side has a potential that is 9 volts higher than the other side. And that difference in voltage is what's going to drive current through the circuit. So I like using water examples. Voltage is like the water pressure that pushes the water through the hose. The more water pressure there is, the faster and harder it is able to push the water through the system. So the higher the voltage of battery, it's able to push more current through the same circuit. So in order to have a circuit, you need a battery that, or some other supply of a voltage, and you need a pathway for the current to travel through. The last official element of a normal functioning circuit, though, is what it is you're powering in that circuit. We've looked at some of the things capacitors do in a circuit. They're kind of a weird case because they're storing energy more so than using it. When you plug something into a circuit that starts utilizing the current and using energy, we typically consider that to be a resistor. And any single thing you plug into a circuit counts as a resistor. Doesn't matter if it's the device called a resistor that you buy at Radio Shack. It doesn't matter if it's a light bulb. If it's in the circuit using energy, blocking flow, it is a resistor. It has some amount of resistance. So electrical resistance is an object's ability to prevent current from flowing through it. What an object's resistance is depends on the characteristics of that object. There is a formula for calculating it. If you, say, are building an object and you wanted to know what its resistance was as you were building it, and you were trying to make it a specific thing, the baseline is, and we'll expand on this one a little more later, this symbol is a constant referencing what the object is made of. So every different material would have a different constant there. We also have the length of the object. This is supposed to be a lowercase l. And the cross-sectional surface area of the object. Those three things, those are three of the four things that don't measurably affect the resistance of an object. And arguably the most important one is, what is the object made of? Because any amount of metal will conduct pretty well. Any amount of rubber will conduct pretty poorly. So we build things out of specific materials so that they have specific resistances. And if something has a high resistance, we consider that to be an insulator. Things like rubber stop current from traveling through them. Or rather, they make it really, really, really hard for current to travel through them. Yes?
I don't understand why surface area is divided, because if doesn't that mean that, like, if you increase surface area, you decrease the resistor
Yes.
capability or whatever?
So
And
keeping in mind, the resistance is how hard it is for current to travel through. Low resistance means it's easy for current to pass. So I'm going to draw two sample wires.
But like, why would something bigger be easier to pass through?
Well, so let's say we have two chunks of wire. And let's say that they are the same length for simplicity's sake. They just have different cross-sectional areas. So the area of this circle is smaller than this circle. If you think of this less as a wire for electrons and more like a hallway with a bunch of people trying to rush through it, which hallway would be easier to get through? The bigger one. Physically, the bigger something is in terms of its diameter, the more physical room there is for electrons, and that just makes it easier for them to get through. Which is probably why, I don't know if you guys have been in any like high science labs recently, but usually the power cables lining the walls there are noticeably thicker than most commercial ones. Power lines, things that happen at power plants, the cables coming off of electrical transformers. If you want low resistance, making the cable physically thicker is usually what you want to do. Because again, physically, you can just jam more electrons through and it's easier for them to travel. Because remember, they don't want to be anywhere near each other. They just really want to get to what's on the other side of the battery more than they hate being next to each other. But they still hate being next to each other. So the more room there is for them, the more they can space out, the easier their job is. So the smaller you make it, the bigger the resistance gets. Now you can still have very low resistance in a very small object, because most wires have a functionally negligible resistance.
Well, that's because it's like better conductor then, right?
Right. Which is arguably why the material matters a lot more than cable size, but they do play an effect. Additionally, the other element here, the length, the longer the cable is, the physically longer the distance the electrons have to travel through. So if L gets bigger, R gets bigger. So material length and surface area are the main things that affect resistance. There is one more, and we will look at a different formula about that. But the last factor, which is actually pretty important, is temperature. An object's ability to resist electricity passing through it increases when it gets hotter. The hotter something is, the harder it is for current to travel through it. Because the warmer something is, the more its atoms are being scrambled by the thermal energy of its atoms, just making them move all over the place. If the atoms are physically jumbled, it's harder for the electrons to use them to travel through the object. I actually might be able to show you something. There's a video that I really like. Now this is magnetism, which is slightly different, but I think it's still a good illustration of the point. And I'll speed through the timeline. Right now, there's electrical current running through the copper spiral, and that is producing a magnetic field that is affecting this piece of metal right here. So, right now, at its low temperature, that block of iron is still magnetic, it still has electrical properties. But, it's about to start heating up, which is why I'm going to jump through the timeline.
Oh, that's why it was spinning too, right?
Right. It is gaining energy from the electricity in the cables, and now it's starting to become rounder and shape itself to the magnetic field. It is melting and becoming softer.
Wait, it wasn't, oh my god.
It's heating up from all the energy.
That's why it's red, right?
It's all right, yes. It is now, it is literally now red hot. And its magnetic properties, and therefore its electrical properties, are currently changing. It's reacting, it's starting to react differently to the field. Eventually,
What is the purpose of the pencil?
just to keep it, I think this person's just trying to adjust it so that it stays a specific shape or rotates in a specific area so that it stays visible on camera. And pay close attention, it's still getting hotter and it's still melting until eventually it reaches a specific core temperature where very hot. At a specific temperature though, it just completely loses its electrical properties. And now that it's no longer exposed to the heat, it's metal again. Now, this is magnetism, which is not the same as electricity, but they are related. So, the hotter something gets, the more it resists. This is one reason why your devices overheat. Because literally when they're too hot, the current can't do its job because the resistance of the system has spiked. Which is why most big industrial computer servers are kept in chilled rooms. And why most of your computers have a fan, which keeps the circuits cool.
That's why I also like eats up for charge.
Say again?
Like it eats up for charge, like when it's hot.
When it's hot, the resistance of the whole thing goes up. And when resistance goes up, current goes down. Because if this is a very small resistor, current can make it through pretty easily. If it's a big resistor, that slows the whole circuit down. And if resistance goes up to a certain point, current will then drop to a certain point. And if the system is just not getting enough current, it just shuts off. And that's if you're lucky. If you're unlucky, something might physically melt. I've heard of computers that physically have pieces melting inside of them, not just the plastic.
It's on fire.
Don't set your computers on fire. I'd say the most important thing from this slide to remember though is this formula, delta V equals IR. This is like the electrical formula. And we know this because resistance, I should write this down. So, like with most things in physics, we have a unit of measure for it, and the unit of measure for electrical resistance is ohms. If you take two resistors and you're trying to see which one resists more, then the measurement is ohms, named after a man named Ohm. And the symbol for that is omega. So the variable the unit this time is the Greek letter, not the variable. Hello?
127.
My lab key, wait, that's Dr. Rutherford's lab right now? My one lab key is in there. That's an oversight, sorry. Welcome. Okay, so electrical resistance is measured in ohms. Ohms symbol is omega. And I tell you this because this formula is so important that it is named Ohm's law. So whenever I mention Ohm's law, I mean V equals IR. And this formula describes the core function of a circuit. Voltage pushes current through resistor. That is the purpose of all circuits. Keeping in mind that the resistor is the machine you're powering.
I did not know that. Wait, what?
Which part is
The resistor is the machine that you're powering? So like in the lab when we did the light bulbs as resistors?
the light bulbs act as resistors because they are taking energy out of the current. Every single thing that electricity passes through is technically a resistor. Which means even the wires are technically resistors on some level,
Or are they like negligible?
but they're designed to be negligible. There are some times where you need like hyper precision and you need to start caring about the resistance of the wires, but for our purposes we don't. We can assume that if it's sold as a wire, it's designed such that its resistance is negligible. But technically speaking, anything current passes through is a resistor. If it conducts well, it's a very poor resistor, which is a conductor. If it resists really well, it conducts poorly, you call that an insulator. Every single thing has a resistance. And thankfully humans have a pretty high resistance because I don't want to get electrocuted. But that's due mainly to our skin, more so than the fact that we're made of water. So yes, in a circuit we have voltage driving current through resistors. Every machine is a resistor because every machine is designed to take energy away from the current. All resistors slow the current down by taking energy away from the electrons. And by design, everything you plug into a circuit to power it is taking energy away from the circuit to power itself. Light bulbs being a pretty classic example. All of the ones in this room use gas instead of a wire filament. So electrons pass through the gas. They leave energy behind inside of the gas, and the gas then starts flowing. So resistance measured in ohms. Resistors take energy away from current. Because this PowerPoint is still a work in progress, I don't think they have any P equals IR examples ready. So, unserved circuit. Nine-volt battery. And 10,000 ohm resistor. How much current is currently traveling through the system?
Um, 9 to the negative 4.
Yep.
1, 2, 40, yeah.
So I'm going to write that as, I'm writing that in terms of amps and milliamps. This is a very typical thing that you could build. 9-volt batteries are commercially available. They're the kind of rectangular ones with the 2 leads on the top. That's a 9-volt. Don't lick them. I don't care what your parents tell you to do.
Wait,
My dad always told me, hey, the battery's low, lick it to make sure it still has charge. This is the only battery where you can get your tongue on both leads.
what happened?
Zap. A very, very small zap, but you can feel it. Probably because your tongue is, covered in saliva.
Wait, you used to do that?
I never did that. I was terrified. By the time Dad was making that joke, I knew enough about electricity to say no. So 9-volt, very common, and 10,000 ohms, also very common. One of the resistors in lab this week was 10,000. It's a very common thing you could buy at Radio Shack, and it's a very common thing for machines to have a resistance about this level. So most commercial circuits have current about this level.
Wait, I'm confused. Why did the battery zap you? There was no, current. Isn't that just the voltage?
Batteries, because batteries have a voltage difference between the 2 sides, and on this type of battery, the 2 sides are both on the top. All batteries, as long as they're not empty, have a voltage difference. And
Like on purpose?
on purpose. And that is at all times. When the battery is disconnected from the circuit, there's no pathway for the electrons to flow from one side to the other. They're always wanting to. As soon as you put a wire from one side to the other, they'll start going.
Wait, are they flowing through your tongue?
Yes. If you are getting zapped, electrons are flowing through you.
Okay. So why can't they be the same voltage?
Electrons always travel from high potential to low potential.
But aren't they being used up? So either way, you're gonna end up with low.
Electrons themselves don't get used up. They're physical matter. They don't go away. What gets used up is the energy that they possess. So when you lick this, you're creating a connection between the 2 sides. Now the electron can start flowing through your tongue and through the saliva on your tongue. The electrons want to go from high potential to low potential. And as long as the battery still has its chemicals in it and it's still doing the reaction that makes it a battery, then this voltage will remain and electrons will keep going from one side to the other.
Okay, what about a battery that doesn't work like that?
Like a standard kind of D-cell shape.
Yeah.
That's still true. These are usually about 1.5 volts. There's still a difference of potential between
Oh,
the 2
this
sides.
is 0 on the other side?
We consider it to be 0. If the battery says 9 volts, that means one side is 9 volts higher than the other, because all voltages are technically a difference in potential. It's not necessarily this side is 9 and this side is 0. It's just that this side is 9 bigger than the other side.
Wait, so that's like a 1-volt battery what you drew? Because it's only, no, the other one. sorry, the one right next to it, next to the 1.5 volt.
This?
Yes, because
Oh.
you said it's a difference, right? So would that be a 1 volt battery?
Now this is, what's the difference between 9 and 0?
Oh, this is 0? I
Yes.
thought it said 10 the whole time.
Oh.
Oh my God, I was so confused. I'm like, I don't know what you're saying.
I do a slash through the zeros to differentiate them from O's.
Okay, that makes, so it goes 9 to 0.
Yes.
Yeah, okay.
As long as the battery has that difference in the two sides, electrons are always going to try to go from one to the other. It's just when the battery's disconnected, the electrons can't force themselves through the air. Because air is a very good insulator, just by its very nature. It takes a lot of voltage and a lot of energy to make electrons move through air, which is usually why you only see sparks when you're about to touch something. Because if you see a spark, that's current traveling through air. Kind of the same way that the light bulbs work. If current passes through the gas, it makes the gas glow. So all electric sparks are current traveling through air. Same as lightning. But because air is a really good resistor, so let's say,
It has a big constant then.
yeah, let's say that air has a really big constant, and the air itself is huge, so electrons that go into the air will dissipate pretty quickly. If the air had like a resistance of 10 million, that would make these numbers 1,000 times smaller. So it'd be functionally negligible. Because air resists really well, a disconnected battery won't really do much of anything. It's only when you complete the circuit that the current starts flowing. And yes, it does, it will flow through you if you make it. We're at the end of the lecture, and I don't want to keep you guys. I think this is a good foundation for what's to come. But the last point I would like you to remember is that electricity is lazy. It will go automatically from high potential to low potential, and it will try to get there along the path of least resistance. So I'm going to draw a parallel circuit real quick. If we built this circuit, where one pathway was 10 ohms and one pathway was 10,000 ohms, the electricity does not like this branch because it's harder to get through than this one. So if we built this circuit, 99% of the current would go down this pathway because it's just physically easier to do so. All electricity tries to find the path of literal least resistance. And I don't mean that in the, oh, it's difficult way. I mean literally the lower electrical resistance number is the pathway that the electricity wants to travel through.
Can it not travel through that at all, or it has to travel?
Some of it will go through here, because if like 99.9% of the electrons are going this way, now this is a really jammed up hallway.
So it's even more hard for like all of them to go through one than for it to go, some to go through the harder one?
Right, this is so jammed up, some of them are still going to go down the other way for convenience sake, but the bigger the difference in resistance is, the bigger the less electricity is going to go down this path.
Okay.
Which is why, thank you, which is why coating wires in rubber keeps us from getting shocked. I don't actually have, no way to. Keeping in mind that there's metal in here going the entire length of the cable, if I am touching the cable, because the rubber has such a high resistance, the electricity doesn't really want to bother forcing itself through the rubber to get into my hand. It will just keep going through the metal because that's easier. And this is one reason why birds can stand on a power line without getting zapped.
Wait, why? Their legs aren't rubber.
Their legs aren't rubbing, but the wire they're standing on is. So, cable, poorly drawn bird feet, poorly drawn bird. Yep. There is metal in the wire. The electricity likes traveling through the metal because that's nice and low resistance. For the current to try to, if the current were to try to shock the bird, it would have to first force its way through the rubber, then go up the bird's leg, through the bird's body, back through the bird's other leg, and then into the same wire it just exited. From the electricity's perspective, there's no point. So it just doesn't. The only time that the electricity would bother trying to shock you through this cable is if maybe a person was touching it and that person was standing on the ground. Because electricity really likes to go into the earth. So this would be dangerous. This isn't.
What about the person touching it on a ladder? Is that still dangerous?
Yeah, because if you're on a ladder, you're still creating a pathway to the earth.
Like conductor. Like the only way
You want to be wearing rubber-soled shoes and rubber pants and rubber gloves and rubber everything.
Okay.
I have been talking a lot of details, not a whole lot of slideshow, and I apologize. I'll make sure everything is nice and compiled and uploaded today. Any questions? Okay. I'll see you guys tomorrow. Let me know if you need anything finishing up tonight's assignment or looking at this information. And see you soon. Stay healthy. Have a nice lunch.
Wait, I do have a question.
Okay.
I don't get outlets. I get the battery, I get high to low, but in an outlet, it kind of just sounds like you're getting voltage from the outlet and it never goes in a circle.
It actually does.
Does it go through the wire again?
Yes. Notice you've got two prongs.
But it's the one wire.
Well, if you cut one of these open, there's multiple wire pieces of metal in here.
Wait, so it's like two layered and then it'll go like this?
Yeah. It's just made narrow for convenience sake, but we have two prongs here and two holes in the wall.
So one is positive, one is negative.
Right. Current goes in through here, goes down one of the two cables into the computer, runs through its system, comes back through the other internal wire, and out through the other prong.
Okay, so then why do some outlet things have like a specific, you know how like some of them you can like flip it, and some you can't?
That third plug.
Oh, not that one. No, I'm talking about the one, actually that's a good question, but no, I'm talking about the one that has like a fatter part.
Right. That is, I've never been formally told why that is, but I'm assuming the bigger piece of metal is the positive one, since that's going to be the higher energy side.
Okay.
Or, technically speaking, the negative side should be the one with the more electrons, so it's probably actually the negative end.
Okay.
The third plug is a ground wire, because if something goes wrong, it's a pathway for the electrons to literally go into the earth and not set things on fire.
So like that's why big appliances have that one?
Yes, the bigger the thing is, the more likely it is to have that third plug.
Okay. Thank you.
You're welcome. Good day. You guys can come in and use the boards for whatever you need.
Running.